Hey, hello there, and welcome back for more Advent of Code. And actually, the last puzzle of Advent of Code 2023. I won't say the last video because, well, I have to admit, like the last puzzles have been very challenging, so I won't have any expectation of finishing this one in just a single video. Although usually days 25 tend to be a bit easier. I probably just jinxed it by saying that. But at least usually they are only part 1 and they don't have a part 2. So I don't know if the tradition still holds, but we shall see. And actually now that I'm saying that the previous days have been difficult, I actually want to remember that a little bit. Because, well, yeah, the day 24 was definitely a challenge. Maybe I don't know if the hardest one, but it was definitely one of the hardest. Or maybe that is just proximity bias speaking. But yeah, I ended up having to use Python and some algebra package, SymPy, to solve this thing. And actually, after I solved this, I checked for some solutions on the Advent of Code subreddit, and I realized that there was I don't know if simpler, but there was another solution that I could have probably done in Rust without the need for an external package to solve a system of equations, and it involved using parallel lines. So in the input there were like parallel hailstone lines that were parallel between each other, and if you have two hailstones that are parallel, well, you can find the plane that contains those two lines. That is pretty easy. You just take 2 points from one line and 1 point from the other and just do a cross product and you get the normal vector. So finding the plane between two parallel like shared by two parallel lines is pretty easy. And then once you get that plane, you know that the intersection line that you want to find goes through that plane, because it has to intersect both of those lines and those parallel lines. And then you just grab 2 other lines and intersect those 2 with that plane. And with those 2 points that you get, you can then draw the solution line. And I think all of that algebra would have been relatively easy, like at least it's all linear algebra. And I think I could have done it like with my very dusty knowledge of university algebra. I think I could have done it in Rust, but I actually like the solution that I came up with of solving this system of equations. And by the way, I kind of like also the aesthetics of the Python notebook. I added like a nice comment. It almost reads like a like an academic paper or something. So I'm pretty proud of this. And yeah, I have to admit, like Python is, I understand now why Python is used so much in academia and also for Advent of Code and things like problem solving in general, because it has these great packages. So it's awesome. And yeah, but what I wanted to see is like from the previous days, yeah, I think all the last ones have been hard. Like this, the 24 was for sure hard. 23 also, it had this very, well, it was computationally hard, day 23, for the part 2. But it required us to like actually model graphs. This day was kind of a 2D grid day, that it looked like a 2D grids problem, but it was actually like a graph traversal problem. Like the grid was like a maze, but this was kind of a disguise. It was actually a graph traversal problem. Day 22 was an easy one. Yeah, this one was the first 3D. No, not not the only 3D puzzle, because day 24 was also in 3 dimensions, but this was the first one of the year, and it was actually quite easy. Step counter was another gnarly one. I was just today I was uploading the video of that, and damn, like part 2 was quite gnarly. We also used algebra there. And day 20 was again like super difficult. 19 aplenty, I don't remember. I think this wasn't so. I don't actually remember this thing. Yes, this one was also, we used some interesting like intersection and thing. Labadux Lagoon was also, like here I learned about that shoelace formula for areas. So yeah, just to wrap this up, I don't know why I'm doing this now, but all the last days have been really challenging in general, so I don't have high hopes of day 25 being easy, to be honest. But let's see what it is about. Let's also take a look at the advent calendar, which is looking really pretty. And we already have 48 stars, so 2 to go, and day 25. Snowverland, okay. Still, somehow without snow, you go to the last place you haven't checked, the center of Snow Island, directly below the waterfall. Okay, so in the previous days we have activated the waterfall that comes flowing down from Island, so we are in the center of Snow Island. Here, someone has clearly been trying to fix the problem. Scattered everywhere are hundreds of weather machines, almanacs, communication modules, hoof prints, machine parts, mirrors, lenses, and so on. So okay, we're having everything from the previous days. What? At least 100 stars? What the fuck? Okay, let's continue reading, but that's a bit alarming. Somehow everything has been wired together into a massive snow-producing apparatus. But nothing seems to be working. You check a tiny screen on one of the communication modules, error 2023. It doesn't say what error 2023 means, but it does have the phone number for a support line printed on it. Hi, you've just reached Weather Machines and So On Incorporated. And so on. Who is this, like Slavoj Žižek? But is this an acronym? WMASO. Who Maso? I don't know if this is a Masoi. If this is a joke, I'm not getting it. How can I help you? You explain the situation. Error 2003, you say? Why, that's a power overload error, of course. It means you have too many components plugged in. Try unplugging some of the components, and you explain that there are hundreds of components here and you're in a bit of a hurry. Well, let's see how bad it is. Do you see a big red reset button somewhere? This is like actual IT, where resetting things always fixes the problem. It should be on its own module. If you push it, it probably won't fix anything, but it'll report how overloaded things are. After a minute or two, you find the reset button. It's so big that it takes 2 hands just to get enough leverage to push it. Its screens then displays system overload. Connected components will require power equal to at least 100 stars. Oh, okay, so we have to bring this number down, I guess. Wait, how many components did you say are plugged in? With that much equipment, you could produce snow for an entire... You disconnect the call. You have nowhere near that many stars. You need to find a way to disconnect at least half of the equipment here. But it's already Christmas. You only have time to disconnect 3 wires. 3 wires. Okay, kind of like those bomb scenes in movies where you have to cut one wire or a couple, and you don't want to blow up. That was also a nice collaborative game that I played some time ago. 8 years ago. But anyway, yeah, it's already Christmas, although Christmas is already past, like 2 weeks ago. But anyway, fortunately, someone left a wiring diagram, your puzzle input, that shows how the components are connected. For example, and this thing. Each line shows the name of a component, a column, and then a list of other components to which that component is connected. Okay, so this is kind of a graph. It reminds me a lot of the, which day was it? Yeah, the one that also was like modules and you send pulses between components. Like it reminds me of that thing. And actually, the graph that we built on day 23, I think it was, yeah, this thing, like, well, then I changed to vectors, but at some point it was a hash map of this, almost this exact shape. Okay, connections aren't directional. ABC, XYZ, and C, XYZ, ABC both represent the same configuration. Each connection between two components is represented only once, so some components might only ever appear on the left or right side of a column. Okay, so these are just like the connections are wires, and this would be like how is it called, like undirected graph, I think is the name in graph theory for these things. Like the edges don't have one specific direction. In this example, if you disconnect the wires between HAF, PLCL, the wire between BBV, CMG, and the wire between these things, you will divide the components into two separate disconnected groups. 9 components, these things, and 6 components. Multiplying the sizes of these groups together produces 54. Find the 3 wires you need to disconnect in order to divide the components into 2 separate groups. What do you get if you multiply the sizes of these 2 groups together? Okay, so a very graph heavy problem, and the inputs is, well, just another graph of many lines. The components are not like very connected. I think this is one that connects to the most, although we are only seeing one direction here, so maybe there's other components that have more connections, but there are many components. Okay. And we want to find, so I guess the initial configuration has everything connected together, and I am also guessing that there is only one combination, like one set of 3 cables that, when removed, separates this like big graph into two graphs. I don't remember like what's the name. I think it's like connected graph and disconnected graph or something like that. But yeah, and I guess that those wires are unique, so that you split the things into, like, there's only one solution and you multiply those 2 numbers and, well, you get the answer. So, okay, interesting. This doesn't sound very easy, I must say. Let's think about it with some late night tea. Rooibos tea, which is very nice. Okay, so I can think of course, a brute force way of doing this, but I don't think, and that would probably work for the sample input, but it most likely won't work for the actual input. And brute forcing is, like, I guess pretty simple. We had to first parse the graph, but once you have the graph with all the nodes and all the edges, we just take all the possible combinations of 3 edges and try them, try removing them from the graph, those like each combination of 3 edges, and see which one of those separates the graph into 2. And once you find that, you get 2 separate graphs, and that's the answer. Well, multiplying those 2 sizes together. But that's kind of a combinatorial problem there, like choosing 3 in between many, and that's a big number of possibilities. Like, are 3. So what is the number of edges? We can probably take a guess of that. I have already opened this thing, so let's start where we always start, and say day 25. How was the name? Snowland something? Snoverland. Oh, or overloaded also? Snoverland? Snoverload. I think I read Snoverland at first. Snoverload, okay. Nice. Snoverload. Okay, and let's also copy the inputs. I could just rename the template, but I will just leave the template exist for like prosperity. I don't know, just to remind myself of how I did this thing. Let's close everything else. This is the actual inputs. Oof, they are already like 1200 nodes, and probably more nodes because there are some that only appear on the right. So yeah, definitely something that's not going to be easy to brute force. And I'm also having my... What's happening here? Do I have some key pressed or something? Well, the browser was not responding. Let's open a new tab for this. I don't know what was happening there. Okay, what was I saying? Yeah, about brute forcing. I don't think that that will probably work for the sample, most likely, but not for the actual input. So let's copy also the sample. And the output that we expect is 54. Yeah, 54. Okay. And by the way, how do you know if a graph is connected or disconnected? I'm not sure, but the immediate way that comes to mind is to do some sort of like breadth first search or depth first search, like the same thing. Like you start by any node and you start searching on all the connected nodes and marking them as visited or not. And once you finish the search, you see how many you have counted as visited. And if that number is the same as the total number of nodes, you already know that everything is connected. And otherwise, you will have like, well, I guess when we have 2 components, we need to find, oh, this is 96, which is like 69 the other way around. Nice. But I'm sure that this is probably on purpose. But yeah, it seems like I think counting, once you have like a graph that you have cut some wires from, counting the 2 separated components would not be too hard. But what I want to estimate is how many combinations there are of things. So the sample, I need to try all the wires. So how many wires are here? I think the way that we can think about this, oh, look at this. This component, for instance, only appears on the right-hand side of many others. And by the way, some, that's interesting also. Some components have 3 wires to them. Oh, that's also interesting, right? Yeah, like if one node has 4 wires in it, we know that's an interesting thing. Like already, there are of course better things to do than brute forcing. But if one node has 4 wires into it, we know that if we cut those 4 wires, the node will still be connected to other things because there is still a wire connecting it to the rest. So unless cutting those 3 wires also lets another node or another piece of things get disconnected from the whole, I think it doesn't make sense to try 3 wires on the same node because like that thing is still going to be connected. And the one that we were looking at, I don't know if it was this, it has 3 wires connected to it, but it also has a 4th because this does not appear in this list. So I am guessing that there's probably no node that has only 3 wires connected to it, because if that were the case, that would be a trivial solution. If a single node had only 3 edges connected to it in the graph, cutting those 3 edges will disconnect that component from everything else, and that would be kind of a trivial solution. So I'm guessing that doesn't happen on the actual input, otherwise it wouldn't be fun. But yeah, what I was thinking about is the total number of wires. So wires in graph theory are called edges. That's the name, nodes and edges. The total number of edges here, unless something is repeated twice, but no, I think the description said that they only appear once, like each connection appears only once in this diagram. So the total number of edges will be the total number of things on the right hand side of like these columns, right? So these 3 nodes here represent 3 edges. These are other 3 edges. This is 1 extra edge. These are 4 edges more, and so on. So we can count those maybe. Let's just count these things. Let's say pretty fast. Print line for input. We're just going to get the lines and then map each line. We're going to do what? We're gonna, they are all 3-letter things, right? So yeah, we can just grab from index, this is 4th, 5th, so from 5 on, you can say something like, hey, give me like splice from index 5 onwards, then split a white space and just count how many of these are, like how many words there are after here, and then we just sum all of this up. And I think that will be the number of edges. And this sum requires a type annotation, sure. So this time we are running something right away, well, after 25 minutes of talking, but not as bad as some other days. It's an overload. Let's print this with the sample first. So what did I want to say? I'm just printing the number of edges, right? 33, okay. And in the actual inputs, 100 times more, 3400. Okay, so my estimation of how many, these are the amounts of wires, right? So my estimation of the amounts of combinations of 3 wires in here, if I'm not mistaken, this should be we can use BC for this. Like the first vertex, or sorry, the first edge can be any of 1 out of everyone. The second one can be 1 out of 32, and the third one should be 1 out of 31, and this is this number. Okay, I think this is the same as 3 choose 33. So let's actually ask Wolfram 3 choose 33 if that was the way you say it, like the combinatorial operation of choosing 3 elements from 33. That is 0, so I guess it's the other way around. 33 choose 3. That makes a bit more sense. It's not this. What am I missing? Probably it's not this operation. Probably. Like, I think the other number that I calculated. So yeah, this is 33 factorial divided by this. When did you use the choose the choose formula? I'm not sure, but let's not think about combinatorics. It's like, I think this number should be the same. Okay, we can corroborate what I'm thinking of by using the combinations method from itertools, which is very useful. We're gonna do something similar. Let's do something quick here. Let's say let edges be these things, but we are not going to sum these things. We are going to split white space and then just collect. And like, I want to have something like this, and we're going to flat. Well, actually, we can avoid collecting. Just split white space and do a flat map of this, and then finally collect vec. So if you do this, the edges, yeah, it's a flat vector. We should have 33 of these, and let's see, this is the number that we calculated. If we say combinations are edges, use iterator, there's combinations and tuple combinations. Combinations, yeah, receives a k. So let's just pass our k, and let's just count these things. So I want to see with a sample. Oh, okay. So the combinations is actually 33 choose k as Wolfram. This is the same number as Wolfram told us, right? 64, 54, 56. Yes, okay. So I'm doing something. Does this work for the inputs? I'm not sure if this would just take a lot of time to compute, or if the count is intelligent. End and count, yeah, combinations. It seems like it's doing something optimized. So let's call this thing for the inputs. Okay, so this is the amount of combinations for the sample. Is a very small number that we can check. But for the actual input, it is, well, 6 billion. It's not that big of a number, actually. It's not that big of a number. It is, however, kind of like 6 billion, for like, consider that one, like, modern computers do like billions of operations every second. But what we need to do in this case for each of these combinations is a bit expensive because it's not just one or a couple of instructions. It's going to be like this whole breadth first search, or this whole search to see if the graph has been disconnected or not. So I don't think that the brute force approach is very good. Now I don't understand why this number is different from what we did here. Like, why are the combinations? Oh, because I guess the combinations, yeah, they don't repeat. So I said, okay, the first one can be any of the vertices. The second one can be any one except the first one, so 32 times 31. But I'm actually not sure why it's a smaller number. It's probably something very simple. Yeah, that's actually, I'm curious now. So Wikipedia, let's choose operation. Okay, I want to combination. Yeah, from a set that has distinct members such that the order of selection does not matter. Okay. Unlike permutations. Okay. So the order in the set does not matter. Did it matter when I thought about that? I'm not sure, but okay, I trust this choose formula, and I trust even more the iter2 combination thing. So that's fine for me. Okay. So I don't think it even makes sense to try out the brute force approach, because I'm just going to get an answer for the sample, but I'm going to get bored waiting for the real answer. So yeah, I don't think it makes sense to just try brute force in this. It might be fun, but we can think about it, like, how would I do this? Or we can Google, maybe. Like, I'm sure that this is something like in graph theory. Like, I'm really not well versed in graph theory or this kind of things. But what we are looking for here is what is this? Like, when a graph becomes connected and disconnected. So what can we look for? Like, how many nodes, edges does it take to disconnect a graph? Very explicit connectivity on graph theory. Look at that. To be removed to always guarantee disconnected graph. What is the average degree of your graph? There must be a vertex of at least. Disconnect this vertex from the graph. Okay, that's a hint. Okay, what would happen? That is something else that we could compute, like how many think about maximally acyclic connected graphs. Maximally acyclic connected graph? Trees. What? Like on a tree, you can just cut one and then you get disconnected thing because it's acyclic, right? Yes. Okay. What was it asking? What will be the minimum number of edges whose deletion from graph G is always guaranteed that it will become disconnected? Okay, I think this is asking kind of the same thing that this problem in Advent of Code is asking, but the answers are not very, it's like, okay, hint. Think about maximally acyclic connected graphs, trees. Okay, so we have this connectivity thing. Maximize number of edges to cut in connected graph. That's kind of the other, like the inverse problem, I guess. We have to minimize, or like, yeah, we have to find not the minimum number. We know it's 3. We know that there is a solution with 3, like removing 3 edges that will disconnect the graph. I am tempted to print out like what is the connectivity of each node, but for that I will have to like build the graph, and I mean that's not that difficult, I guess. But like, how would I, like, it doesn't make much sense because I'm not even sure like the representation of the graph that I will choose will make much sense for like the actual solution. But maybe, I mean, maybe we can try that. Our graph will be a hash map of just have string reference to a vector of string reference. And we are going to go both ways. Whenever we see a wire, we are going to add it like both ways. So do a new hash map here. And then we are going to just go for for line in input lines. We are going to do this kind of thing, but let's say and remove this and this formats. So what are we going to do? We are gonna grab the key. Well, the key is like the name of a node. So let's say node 1, node A, whatever, is gonna be line the first 3 things, sure, and then first 3 characters, and then we're going to iterate this for node B in these things. We are going to say, okay, the node A connects to node B, and the node B connects to node A. So how do we do that? We're going to say graph. Let's see if I have finally learned how to use the entry The entry API for maps, I don't think I have, but let's see. Give me the entry for node A, and we can say or default, because we're going to have an empty map. Yeah, or default. And then should be now a vector. We can now push into this vector and just push node B. Does this compile? And node A, the size, oh, okay, yeah, take a reference to that. So it's a string reference. Let's remove unused imports. Okay, this does compile, and then do the same thing but the other way around. We're going to say that the graph is like this. So do we, yeah, is this the correct graph? We can maybe just print it, right? For node and edges is not the best name, but whatever, in graph iterator. Whoops, just, yeah, we have already seen the combinations, no need for that. Gonna print, just say node connects to, and then just print the edges joined by a comma, which is kind of the input again, but now things should appear like twice. And I just printed the input. Let's print the sample. So now it is like the complete graph that we were seeing here. And for example, let's take a look. For example, this LHK doesn't appear on the left-hand side of here, but LHK, where is it here? Here it is. So yeah, it's connected to 4 things, and I presume they are these 4 things. So I think this is the correct graph. And we can see already in the sample there is no node that has only 3 edges, because that would be a very trivial solution. And I guess if we print with the actual input, there are some nodes that are connected to more, but I'll bet you that there's no thing that has, of course, like 3 nodes. We can check that maybe. Say print line min connected node, and we're just going to print graph values. Get me the min, or just map into this is gonna be what, a vector, so let's just have the length of this thing, and give me the min of this, and just unwrap this thing. We know that there's gonna be a minimum. Okay, 4. So even in the input, of course, there is no, this was the real input, yeah. There's no trivial solution. Okay, makes sense. But we have also seen that there are some like things that have more connections. But okay, how do we go about this? Connectivity. This is kind of from a book, it looks like. We have seen examples of connected graphs and graphs that are not connected. While not connected is pretty much a dead end, there are much to be said about how connected a graph is. The simpler approach is to look at how hard it is to disconnect a graph by removing vertices of edges. We assume that all graphs are simple. I don't know what is simple, but whatever. Cut points. I don't know if I should cut the video and just read some literature of this and then come back. Let's give it, like, it's 45 minutes. Let's give it like some 10 or 15 minutes of reading. And if I cannot find anything interesting, we'll call it a day or a session at least. If it's possible to disconnect a graph by removing a single vertex called cut point, we say the graph has connectivity 1. But these are vertices, not edges. So, okay. If a graph G is connected, any set of vertices whose removal disconnects the graph is called a cut set. G has a connectivity K if there is a cut set of size K but no smaller cut set. If there is no cut set and G has at least 2 vertices, we say G has connectivity n-1. Okay, definitions, blah blah. As you should expect from the definition, there are graphs without a cut set. The complete graph Kn. Complete was when, I think, like when all the nodes connect to all the other nodes. So vertices, nodes are vertices. Okay. We do the same thing for edges. That's what I want to know. If a graph G is connected, any set of edges whose removal disconnects the graph is called a cut. Not a cut set, a cut. Edge connectivity K if there is a cut of size K but no smaller cuts. Okay. G is K edge connected if the edge connectivity of G is at least K. The edge connectivity is denoted lambda of G. Okay, and there's a square here that I will assume is just like a glitch. Well, this is what we already have observed, I think. Any connected graph with at least 2 vertices can be disconnected by removing edges. By removing all edges incident with a single vertex, the graph is disconnected. Thus, lambda G is less than this Greek symbol, I think is rho or something, where rho G is the minimum degree of any vertex in G. Know that rho G is less than n-1, so okay. What is this thing? This, I guess, is the vertex connectivity, but okay. Theorem, okay, proof. Well, I don't know. Do we have algorithms here? I think we want Menger's theorem. Okay, this is a very textbook. Ooh, look at that. Cool pictures. But we have some interesting jargon from here, which is cut and cut set. So let's look for what do I want to look for? Like graph theory finds minimum cuts in graph. I don't know why I said graph theory first. Oh, look at that, a YouTube video of 4 minutes, just like my videos. Maximum flow algorithm. Haven't I already had something like maximum flows in minimum cuts? Okay, that sounds a bit more promising. Oh, look at that. Yeah, those are cuts. A graph and 2 of its cuts. The dotted line in red represents a cut which with 3 crossing edges. The dashed line in green represents one of the minimum cuts of this graph, crossing only 2 edges. Yes, this is what I want. Do we have some... we don't have some code here, but... Okay. Minimum cut problem is undirected. Without terminal nodes, no negative weights. Yeah, this is not a weighted graph. Like, weighted means that each edge can have different weights. Oh, look at that. Can be solved in polynomial time. Yeah, using the Stoer-Wagner algorithm. Yes, give me an algorithm. In the special case when the graph is unweighted, Karcher's algorithm provides an efficient randomized method for finding the cut. In this case, the minimum cut equals the edge connectivity of the graph. Yes, the edge connectivity. Interesting. Like, this seems pretty promising. Okay, so this is a more generalized problem. We don't care about this, like k-cut, like cutting the graph into k pieces. Okay, and there is a similar problem where you have like source and sink nodes flow network. Okay, yeah, because this is actually a very real problem in like telecommunications and things like that. When you have like a distributed system of machines connected, or maybe like a power grid or something like that, you have many nodes connected to that thing, and you want things to stay connected even if some edges fail and are cut. Like, I have a friend of mine who works like in like internet, providing internet for basically for a company that provides internet for internet providers, so like big pipes of internet. And yeah, I guess they deal with this sort of problem of keeping the graph connectivity high. So if any of those cables, I don't know, international cables that go through the ocean maybe gets munched by a shark or something, we still have internet. But okay, well, the links I opened were for the Stoer-Wagner algorithm, the Karcher's algorithm, and edge connectivity thing. So what is chi-edge connected graph? My cat sleeping below my computer is moving things, so please don't do that. Yes, this is interesting. In graph theory, a connected graph is k-edge connected if it remains connected whenever fewer than k edges are removed. The edge connectivity of a graph is the largest k for which the graph is k-edge connected. Great. So I guess the graph that we have is 2 edge connected. So if you remove any 2 edges, it's still connected. And look at this. This is a pretty simple graph, and it's also 2 edge connected. That's interesting. So if we cut any 2 edges, the graph never becomes disconnected. And you can see that all of the nodes on this graph... Wait, if I cut these 2 edges, this vertex becomes disconnected. The smallest set X whose removal disconnects G is the minimum cut in G. Well, maybe when you just leave one vertex disconnected, it doesn't count for this thing. Okay, I think that this is not a case that will happen with our problem, because I'm pretty sure like when we disconnect the graph, it's not going to be disconnected by only one. Actually, we know that because the minimum connectivity of a single node is 4, and we need to make a cut of 3. So okay, I think I got the idea that Carter's algorithm was like a special case when the graph is unweighted. So maybe this is the simplest of the two, but we shall see. Randomized algorithm to compute the minimum cut of a connected graph. It was invented in 1993. Contraction of an edge. Multigraph. What? I love this thing in Wikipedia that you have the preview of the linked articles, and it's like, yeah, multigraph, what the hell is this? And the image of a multigraph is already like pretty self-explanatory. Like when you have nodes connected by multiple edges. My mouse is a bit shaky. I think it's because I got rid of the mouse pad, which was very deteriorated, but it doesn't read very well on the table. But it's okay. The global minimum cut problem. ST, what is this thing? What I was reading. Iteratively contracts random chosen edges until only 2 nodes remain. Those nodes represent a cut in the original graph. By iterating this basic algorithm a sufficient number of times, a minimum cut can be found with high probability. What? So it's a randomized algorithm. That's interesting. That I've never done one of these. High probability of finding it. Like it's contracting. So I guess there is an idea of contracting to, well, an edge can be contracted. Yeah, look at that. Also, the image here is beautiful. Like this gets contracted, and like U and V gets together, and I guess everything that was connected to it remains connected to the new node. Iteratively contracting random chosen edges until only 2 nodes remain. Yeah, but this is not, that doesn't sound like a good algorithm for our case, right? Two non-empty disjoint sets S and T, with where the union of those is V. V is the set of vertices, I guess. Yeah, the graph. So this is very like typical nomenclature of graph theory. Like a graph is a set of vertices and a set of edges. So okay, an ST partition. The cut set of a cut consists of the edges yeah, okay, where U and V. Okay, yeah. This is very math nomenclature, like the edges UV belonging to the edge set, where U belongs to S and V belongs to T. Okay. Size, weight of a cut. An unweighted graph is the cardinality of the cut set. Yes, okay. Yeah, I don't know if I will go with this contraction algorithm. Only 2 nodes remain, at which point there is only a single cut. The key idea of this algorithm is that it's far more likely for non-min cut edges than min cut edges to be randomly selected and lost to contraction. Okay, so when you contract a node, you lose the edges that are connecting those two. Sorry, when you contract an edge, you lose all the edges that were connecting those two vertices. Okay. And the key idea for a non-min cut edge, randomly selected and lost to contraction. Since min cut edges are usually vastly outnumbered by non-min cut edges. Okay, yes, this makes sense. So because the min cut edges that we want to find, actually we know that there's only 3 of them. Subsequently, it is plausible that the min cut edges will survive all the edge contractions and the algorithm will correctly identify the min cut edge. Okay, so if in the end you get to 3 edges, successful run of a Gaussian algorithm and a 10 vertex graph, the minimum cut size has size 3. Wow, this is a very interesting algorithm. So actually here in this graph, this initial graph, the cut size was also 3. And it's like it's 3 here, like very visually visible. Like you can see if you cut these 3, you disconnect these 2 like pentagram thingies. But the idea is that the algorithm doesn't have to fall into one of the cut set edges. So if it falls into one of those 3, you don't get the answer. But the chance of that is low. But I don't know, like at the size that we have how many nodes do we have? So let's print actually the amount of nodes. Well, on the amount of edges, well, we have already done that previously, but I probably lost that output. But it was like 3,000 something. Yeah, 3,000 something edges. So what is the probability of not choosing to contract? Oh, it's interesting, of not choosing to contract the successful edges. But the thing is, when you start contracting things, you're going to start like having some very connected nodes. Like these nodes here have like 3 connections, so it's much likely to, when you choose an edge from here, to choose one from these things than these 3. So that's also interesting. So yeah, and the contract procedure takes the graph, and while the size of the vertex set is greater than 2, choose uniformly at random. So we will need to have also a random number generator, because Rust doesn't have one of those by default. The only cut in G. I like how this pseudocode is like, oh yeah, return the only cut in G. Yeah, okay, while the amount of vertices is greater than 2, so when you end up with only 2 vertices, and I guess this is G with G contracted by E. So I'm assuming that this is the case here. Okay, so it's kind of understandable. I don't know if it's like, it's a very interesting algorithm to implement for sure. Like it's really interesting. You would have to do this iteratively and choosing things at random. Yeah, it's kind of interesting. When the graph is represented using adjacency list or adjacency matrix, a single edge contraction operation can be implemented with a linear number of updates to the data structure for a total number of OV squared. Okay, yeah, this thing runs in OV squared. Well, this gets complicated again, like more algorithms constructing a minimal spanning tree in a graph where the edges have ways. What? E pi? Oh, random permutation pi, not the number constant, the circle constant. Removing the heaviest edge on this tree results in 2 components that describe a cut. Yeah, the thing about this this thing, adjacency matrix is maybe an interesting way of representing this. Like this, if I remember correctly, is like a matrix with, you have well, 1 row for every node and 1 column for every node, and in each cell of the matrix you put if those 2 nodes are connected, basically. But how you would contract that thing, I'm not sure. An adjacency list used to represent a finite graph in general list width. Yeah, okay. Yeah, this is the way that we are doing things now, or more or less this adjacency list. Success probability of the contraction algorithm. In the graph GVE with V vertices, the contraction algorithm returns a minimum cut with polynomially small probability. Polynomially small. So okay, in our case, since we know that the minimum cut is 3, when we do this algorithm, if in the end we have 3 connections between those 2 last edges, then I don't know what is this, the random edge choice. Well, I don't know what this other reference to the cross-style algorithm. But in our case, if we do this contraction a bunch of times and we find a case where the last 2 vertices are connected by 3 edges, we know that that is the solution, those 3 edges. But we need to still have, like, the edges have to be identified by some number or something, because they have to, like, we are not interested in the number of the min cut number. We already know that number, it is 3. We are interested in the edges themselves. So, okay, recall that every graphs have cuts. What is a cycle graph? Oh, no nice picture for this. Oh, it's this thing. Great. Okay, so I don't know if this is the way to go. Like, it sounds like a super fun algorithm to implement, but this randomized thing idea, and like the thing about this is that once you get to the end, like, okay, you know that the minimum cut size would be 3, but we already know that. We care about the edges, so we would have to, like in the contract algorithm, we will need to identify all the edges with some, well, that shouldn't be that complicated. We give an identifier to each edge, or like an index in a vector or something, but still, it's like, I think it's not very ideal. So let's look at the other algorithm, Stoer-Wagner, Wagner, I guess, this is German, and Stoer, I have no idea how to pronounce. It's a recursive algorithm to solve the minimum cut problem in undirected weighted graphs with no negative weights. Okay, the weighted thing is not necessary. Again, 95. So these things are from, you know, the times when the internet was getting very big. So I wouldn't be surprised if these things were like related to, like, these algorithms were developed in relation to that. Is to shrink the graph by merging the most intensive vertices. So this is kind of similar until the graph only contains 2 combined vertex sets. Isn't this kind of the same thing? Chosen at its will. What? Then the algorithm shrinks the edge between to search for non-ST cuts. In all phases will be the minimum weighted cut of a graph. Okay, well, here we have a more like code-looking pseudocode. A bunch of, oh, look at that, actual code, C++, yeah, look at that. Adjacency matrix implementation of Stoer-Wagner min cut algorithm, running time v squared, so the size of v, the amount of vertices cubed, sorry, and the amount of vertices that we have was the amount of nodes. I don't know how many they were. Like we know the inputs as to 1200, but we can print that. Nodes. How many nodes do we have? It's just the graph length, because we are doing this with an adjacency list. So okay, it's this time cubed, which is big but not so big. Title of something. Syntax error, thanks. Standard calculator. So, well, it is a bit long, 3 billion. Maybe this is not the greatest thing to do, but I mean, we can try it. Should I try to read this or try to understand what the algorithm, or more contract things? Some mem set. So it's not just this thing, right? It's not just pair of things. So it's a bit of code to understand. Look at that C style C++. Okay, so should we try to understand this algorithm now? V1, a min cut of a weighted graph having a min cut weight of 4. So okay, in things that are weighted, you care about the weights, I guess. A cut. So I don't know if this is also like a randomized. It says that it's a recursive algorithm, and I don't know if it's using some randomly selects nodes. Okay, well that is the only case of random in this article. So the C++ thing is not using, I don't think it's using any random, or let's look for R&D. No, okay. So I don't think there's random things in here. Okay. Let's try to maybe understand what this algorithm does. Yes, a minimum cut is the cut for which the size of weight of the cut is no larger than the size of any other cut. Yes. And this is cuts of edges. So it is what we, for an unweighted graph, the minimum cut would simply be the cut with the least edges. Yes, that is what we want to find. For a weighted graph, the sum of all edges weight of the cut determines whether it's a minimum cut. In practice, the minimum cut problem is always discussed with the maximum flow problem, and this is in violet color. So I have already fallen in here in a previous, but I think I closed this immediately. But yeah, this is also makes me think of like networks like the internet or like electric grid, where you want not only to have connectivity, but you want to have like big pipes and big like possible like download speed. So you need like you need to provide, I guess, flow for many nodes on a network. So it makes sense that all of these things are related. The maximum capacity of a network. The minimum cut is a bottleneck in a graph or a network. Okay, very interesting. Let GVDs be a weighted undirected graph. So I guess W would be the set of weights. Suppose that. Is in S. What is S? Cut of G. Where does Stoer-Wagner minimum algorithm? So I'm being stupid, but here it's like T is in S, but it doesn't start saying what S is. Or T is in S. Finding an S and a T in V and an ST min cut. For any pair ST, there are two possible situations. Either ST is a global min cut of G, or S and T belong to the same side of the global min cut of G. Okay. Therefore, the global min cut can be found by checking the graph G intersection with ST divided what? After merging the vertices S and T into the new vertex ST. V. Right, if S and T both have edges to some... okay, then the weights of the edge from the new vertex ST to V... yeah, okay. Okay, so yeah, if you are contracting two vertices and those two vertices connected to another vertex, you sum those weights. So I guess even though our graph is not weighted, this algorithm is weighted, so we would need to represent that. The algorithm is described as this: minimum cut phase, GWA. I guess G is the total graph, weights are the weights, and A is, I have no idea what. It's distinct to V, and I like how V is not a parameter in here, but I guess V is the vertex set of G, sure. Add to A the most tightly connected vertex. Tightly connected vertex, I guess, would be a vertex with the minimum amount of connections. I don't know. Store, so while A is different than V, store the cut in which the last remaining vertex is by itself. The cut of the phase. Shrink G by merging the two vertices. Added last, the value of the cut to the phase. What? Is the value of the mean ST cut. Minimum cut, while V is greater than 1, we do the minimum cut phase. So I guess I want to know what A here is. It's lighter, the cut to the face, cut of the face. Okay. Like this pseudocode is not something easy for me to understand. Works in phases. The minimum cut phase, the subset A of the graph's vertices, grows starting with an arbitrary single vertex until A is equal to V. In each step, the vertex which is outside of A but most tightly connected with A is added to the set A. But most tightly connected to... okay. This procedure can be formally shown as add vertex set not connected to A such that W, the weight between A, but A is a subset of the graph. Most tightly connected. Weight between with A, Y not belonging to A, okay. Where is the sum of the weights of all the edges between A and Y, okay. So in a single phase, a pair of vertices S and T and a mean ST cut is determined. Okay. So we do that until we have all the vertices. after one phase of the minimum cut phase, the two vertices are merged as a new vertex. So okay, so in a single phase, a pair of vertices S and T, and the minimum ST cut is determined. So because you're starting with a vertex, and then you add the vertex that is most tightly connected to all that subgraph. Okay, I guess. And since it is the most tightly connected, it will mean that, yeah, surely those things won't be part of the minimum cut set. But then the last S and T vertices, why do they determine an ST cut of C? So I'm not really sure, like, if I understand this idea of an ST cut. ST cut is if it's only one of S or T is in S, the minimum cut G. I'm pretty sure that S is not being defined here before. Like it just starts talking about ST cuts chosen. Okay, but let's try to roll with this. Example. This is a Wikipedia article and says this section refers to figures 1 to 6 of the original paper. What? And the paper is a simple mean cut algorithm. Yeah, sure, very simple. Come on, Stoer and Wagner. Man, I wonder if I will end up pirating a paper just to understand this thing. Like really, but this does not belong, like this sentence does not belong to a Wikipedia article. It's like this section refers to figures 1 to 6 in the original paper, but how can you refer to figures on a paper and not have like the figures in the Wikipedia article? It's like, this is a very bad article, I think. The graph in step 1 shows the original graph G and randomly selects node 2. Like, okay, it talks about an image that I cannot see. Do I have like the paper? PDF. Yeah, awesome. Awesome. So yeah, all of this is like from a paper. Correctness and beautiful. A simple example, yeah, figure A. Beautiful, okay. So we have the paper, great. And we have the Wikipedia article, which I don't know if the Wikipedia article is just pieces from the paper. It's like, why would I read this instead of reading the paper? Randomly selects node 2 as the starting node. So it's, I don't know if this is also like a randomized algorithm or just saying random is the same as saying, okay, pick any and you can pick the first and it will be nice. Select node 2 as the starting node for this algorithm. So node 2 is this node, and of course nodes and edges have numbers as their identifiers, of course. And the weights are these things, edge weights. the graph after the minimum cut phase GWA with A equal to, okay, so A is a node, right? Not, yeah. And also, like, this nomenclature, I'm pretty sure that it talks about nodes, but the set of nodes is called V, like long V. Like, why is it called that? And like V refers to, like, comes from vertices. So it's like the jargon, the nomenclature of things is not consistent. A only has node 2. The heaviest edge is edge 2, 3, so node 3 is added into set A. Okay, so we need to determine which of the other, we start with 2, then we need to define, see which of the other nodes is the most tightly connected, and since it's only one vertex, one node, it will be the maximum weight. Since we have undirected, unweighted graph, that will be just anything that is connected to 2 in our case. So, okay. Next, A contains node 2 and 3. The heaviest edge is 3, 4. Thus, node 4 is added to set A. So, just the heaviest edge is considered. That doesn't make much sense, but let's take a look at the graph. Then we're going to have 2 and 3. Yeah, and between 2 and 3, like, we just look at the edges outwardly, I guess, and this is also like the heaviest edge, so this is the thing that is mostly connected to this. But I mean, if we had, like, after we add 4, we will be looking at all of these edges. Like, why did we add 4 here instead of, well, there is no other node that connects to many of them, but once we have 4, we start to have cases. Well, no, actually before we started with 2, but why didn't we add? No, sorry, I'm getting confused. Once we add 4, this 7 looks like a best candidate because it connects to 3 and 4, and it has total weight of 4. So is that what happens? 4 is added to set A. By following this procedure, there's 2 nodes. Come on, like, the next one was going to be an interesting one, and I think 7 was. Is it explained here? And the induced ordering A, B, C, D, F, S, T of vertices. Okay, so here we see the order. So it was A, B, C. Yeah, then D. It was the 7 because it had 2 weights. Okay, thanks for giving me more information than the Wikipedia article. Thanks, paper. Then E, I guess because these weights add to 5 and no other thing added more than this. F and yeah, S and T are the two last nodes that are added. The first cut of the face corresponds. I don't know why this is cut of the face. Like the grammar of this like breaks my head. To partition 1 and 1, 2. Okay, so we left S and T for the end, which is node 5 and 2 and 1. 5 and 1. So what does that mean? The first cut of it corresponds to partition 1, and then all the rest of it with a weight 5. So T is the last one, so I guess, I don't know, like do you just sever the T node from all the rest and see what happens? With 5. So okay, then you contract, I guess, S and T, and this now is nodes 1 and 5 contracted, and we added up these two 2s into a 4, and we lost these 3 for some reason. So okay, the minimum cut of this thing, I guess, is going to be, I don't know, this one, which is like 4. It looks like it, right? I guess so. Great. I almost like want to like print this graph somehow, but it's like 1500 nodes, so it's going to be giant. And see like if visually you can find 3 edges. Probably not. It's gonna be a mess, and it's not guaranteed to be like a planar graph, so yeah, it's probably not something that you can just see. Corresponds to the partition. Okay, so the graph after the second minimum cut phase. So we started again with node 2, that's fine. And we went A, B. Okay, so the maximum connected to this was this node now. Great. Then C, makes sense. Then D, okay. E, and then S and T. And now we then going to, okay, so what we do is we contract S and T. That's what we do. We contract these things. After the third, yes, corresponds to this. The third cut of the face corresponds to partition 7/8. Wait, why did the first partition correspond to the partition 1 and then this doesn't include the 5 with a weight of 5? The second cut of the face corresponds to the partition 8 and then everything else with a weight of 5. Okay, I'm not entirely sure about how that works, because now it changes, the partition becomes 7/8 after the third minimum cut phase. So okay, so we started again with 2, then B was this again because this didn't change, C was this again, D, this was S and T, and then okay, if we cut this T, the weight of this is 7, yeah. Okay. The weight of 7. And then we contract this 2. Right, so we're going to contract this 4, these 2 are going to add up to 6, so this is what we see here. At the fourth and fifth minimum cut phase, respectively, the cut of corresponds to 478. Okay, so we end up again with, so it goes A, B, and C. Still, this is the mostly connected thing. Then S, and then T. So we sever this thing, still connected by 7. The fifth cut of the face corresponds to, okay, so here we go, A, B, S, and T, and this is a bit more interesting with a weight of 4 here, which is weird. But these are like the original vertices too. Okay, and you're going to join this and this. So you end up with this, and you go again A, S, and T. You start now you start with this one, okay, and then this is the last one. After the 6th and 7th, respectively, the cut of the face corresponds to the partition 1, 5 with a weight of 7. Yeah, the last cut of the face corresponds with partition 2. and V without 2. Yeah, okay. Its weight is 9. The minimum cut of the face G is the 5th cut of the face, and the weight is 4. So the 5th one of this was the minimum weight. Wow. Interesting. It was this one. When we cut 3 and 1, which was these things. Wow. Really cool, really interesting. Okay, so this definitely does feel much better than the brute force algorithm that we did. And yeah, just then it goes to the acknowledgement and great, okay. I think I kind of followed what's happened here. Not just entirely so, but I'm very glad that then we have proof of correctness. I don't care about the proof. Running time of minimum cut is equal to the added running time of V minus 1. Like, okay, it's polynomial. That's what we care about. To make it easy to select the next vertex to be added to the set A. Most tightly connected vertex. Execution of the face on vertices that are not in A reside in a priority queue based on a key field. I guess in a Fibonacci heap. Okay. I don't know if we will like go into interesting optimizations. I just want something that works really. It's been already 1 hour and 40 of learning about min cuts and German sounding algorithms, and we just coded this thing. Okay. Global min cuts. It returns an int and a vector of ints, which I guess this is kind of what we care about. This vector, I will guess, is the vector of nodes, of the nodes in this adjacency matrix. Yes, and it starts with this best, which is just okay, like the default return value. Cool. Beautiful. Vector of vector is okay. We start with, what does this mean? We initialize this with an empty vector, no, with a one vector of one element. Got those beautiful variable names. S and T. It's interesting also that it uses size T for some things and ints for others. That is very C++-ish to do. Is less than n minus pH. So we're going from pH from 1 to n, and then we are going from 0 to n minus pH. Okay, so we are iterating like in a triangular way this matrix, which does it make sense? I guess because it's an adjacency matrix, and if it is like it's undirected, the weights are going to be symmetrical. W, so this is this, int min. If you have a priority queue, we change an quadratic thing with a logarithmic thing. E and V, okay, beautiful. S is T, T is the max element. And this max element, I guess, is gonna be, oh no, I guess it corresponds to, here it's using the namespace std, so I guess max element belongs to the std namespace. Great. And it's also using bits from standard C++ header. Great, 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 great. Okay, wait, is this all? Like, is this, because this is not calling any, like, the contract and things? What the hell? Like, this is very compact code, and I wonder if this is like, because why does it end here and citation needed? And I don't think the code below work, it doesn't even appear to be valid C. Below is a concise C++ implementation, and there's a link here. Competition templates library. And I like that this is, it says, I don't think that code below works. It doesn't appear to even be valid C. A comment from 2016. Great. But yeah, this is another code. Great. This is very readable thing, very readable code. And here's a GitHub global and min cut, and yeah, it's exactly this thing. Stress tested together. That's great. Okay, I have more trust in this than this C code. Even though it's a very succinct and compact way of concise implementation of this thing. But we have these 3 nested for loops here, so you know you can kind of see the cubic nature of this thing. So we need to do something kind of like this. When do we put things into best? That's kind of best is the minimum between best and these. Great. So since we have the minimum weights, that's interesting. We are gonna, okay, so once we have the cut, the minimum cut, we should also know like how many, like when we do the cut, we were following this on the great paper. This is the 5th case. When we do this cut, we actually kind of know that how many components are in here. we have 4, and this, like this number, if this is 4 and we started with a graph of I don't know how many, like 8, so this is 4, we know that the other number is also 4 because it's 8 minus 4. And actually the number that we have to multiply, the two numbers that we have to multiply is like two numbers belonging, like this was the amount of nodes, this giant number. So if we assume like half and half, we just multiply those two numbers together and see, we could try that and see if this is the correct answer, and then sort of do a binary search, because it won't be, well, it is, but the amount of possible answers is not so astronomically high. That's interesting. I don't know why I'm still in DC, but okay. I think I'm going to maybe this video is already like too long, and I want to take a little break and think about this thing a little bit more. But I think we are going to try to implement this Stoer-Wagner algorithm instead of the Karcher's one, even though this sounds a bit like more esoteric and fun, because it's a randomized algorithm. But I mean, this one sounds a bit more like, yeah, this gives you the answer directly once you do it. And we have a very, very, very concise implementation. So we can maybe even like copy this concise implementation into Rust and not have to interpret this very much. And yeah, just see what happens if we reuse this. There are some interesting things in like that come from C++, like for instance this assignment here, I think it's doing implicitly a copy of a vector, which in C++ is like, yeah, okay, you want a copy, have a copy, you know, no problems. In Rust you would need to, like if you do nothing, you would be moving out of the matrix, and you would get a complaint from the borrow checker, so you would need to like clone this thing more explicitly. But yeah, this would be like the vector of weights, and then I see that the vector of weights is modified. All the vector of weights is modified. It's interesting. Yeah, this is very concise, but I think I can probably understand what this does. And even if I can't, I can just copy. And we just need to make the adjacency matrix for our graph, just feed it into this thing, and then we'll have a minimum cuts. And then once we have a minimum cuts, we can just make the cut in the graph, like remove those, like this should be, wait, but what are these ints actually? When we put things in the best, oh, we have the S and T nodes. We have the S and T nodes, but we don't keep the edges that were cut, right? We get the S and T nodes, I think. Co, I guess it's like column or something like that. It's a vector of vectors also. It's also a vector of vectors. So okay, wait, if this is also a vector of vectors and we are just initializing it with like an empty, not an empty, single elements, do we then change the co? Let's search for now highlight all of the codes that are whole words. And then we insert things into code, okay. So we're inserting things into code. So here, I'm actually not sure, since code is a vector of vectors, I'm not sure if this best thing is a vector. Yeah, we're giving it a number and then a vector of numbers to initialize a vector. So I don't know what C++ like constructor does with that. Like this is so succinct that it's like really difficult to follow what's happening. But okay, I think I'm going to cut the video now. I have an idea of what to do on the next session, which is to implement this little fella Stoer-Wagner algorithm or some approximation of it and see if we can have a minimum cut of 3 wires for our problem. And sorry for the long video and not much coding, but I just needed to learn something for this. So if you have been watching this very boring thing so far, I hope you at least learned something new like I did for how to cut a graph and find the minimum cuts on it. So that will be it for this video, and as usual, as always, if you have been, thanks for watching and see you later. Bye.